The equivalence principle has been mentioned yesterday and today already. I will try to I will show some instances of the equivalence. Well, first I will explain what the equivalence principle means. Then I will, in the second part, show how the equivalence principle is enforced or can be proved in univalent foundations or in univalent type theory. We have already mentioned Leibniz law. This is one part of Leibniz law. It says that identical objects satisfy the same properties. The other part would be the inverse. Objects that satisfy the same properties are identical. I will only talk about this one. So this is a basic reasoning principle in logic. The problem with this principle is that it's purely logic. It doesn't take into account what kind of objects x and y are. So it's very weak in that sense that it's true for all objects, or it is assumed for all objects x and y. But in mathematics, when we reason, actually we want here a weaker hypothesis. We want that an invariance of certain properties, or of all properties, not under equality, but under a weaker notion of sameness. Okay. So what do I mean by that? Reasoning in mathematics should be invariant under an appropriate notion of sameness that takes into account the nature of the objects that I'm looking at. For instance, when I compare numbers, I compare them up to equality. So this is, say, a base case, or when I compare functions. But when I compare sets or groups, I don't compare them up to equality, but up to isomorphism. And I want my reasoning about groups to be invariant under isomorphism, not just under equality of groups. And when I go up, let's say, a categorical hierarchy, I get weaker and weaker notions of sameness. So in set theory, this equivalence principle is not enforced. That means that I can find statements that are not invariant under an appropriate notion of sameness. For instance, here I have two categories which are equivalent. So this symbol here means equivalence of categories. And I can find a statement that is true for one and false for the other category. Okay. One such statement would be the category C has exactly one object. This is a statement that is valid, but is not mathematically useful, maybe. So a mathematician would never make such a statement. And one goal of logicians and mathematicians, here Michael Mackay, has been to find a language that does not allow for such mathematically useless statements. For instance, so Mackay, in his paper Towards the Categorical Foundation of Mathematics, he says, the basic character of the principle of isomorphism, so he talks about isomorphism, but we will more generally call it principle of equivalence, is that of a constraint on the language of abstract mathematics, a welcome constraint because it provides for the separation of sense from nonsense. So, put that a bit differently, a goal could be to have a syntactic criterion for properties and eventually also constructions that are invariant under equivalence. Okay. By the way, feel free to interrupt me whenever you want to. Let's stay with the example of categories for a while. We had this statement that was not invariant under equivalence of categories. Where exactly does the non-invariance come from? Why is it not invariant under equivalence of categories? Because it refers to equality of objects. This is a problem in the sense that forbidding to refer to equality of objects So we want to have a constraint on the language, so we might say, okay, let's exclude equality of objects. So how can we do that? We have, even in the definition of what a category is, we mention equality of objects, namely when we compose, when we say what composition in a category is, we say that two arrows, G and F, in order to compose them, they need to be compatible in the sense that the source of G must be equal to the target of F. And only when this hypothesis is satisfied, then the composite G after F exists. So definition of a category refers to equality of objects, at least this definition does. How can we repair this, this definition? Can we give a different definition of category that does not refer to equality of objects? We can, if we use a logic or a language of dependent types. So this logic or language of dependent types must encode this information that the source of an arrow is the same as the target of another arrow, somehow by using these dependent types. So the definition of categories using dependent types or dependent collections can look like this. We say that a category consists of a collection O of objects. This is this is normal, nothing changes. But then instead of having one collection of arrows and maps source and target that indicate the source and the target of each arrow, we will have a family a family of collections of arrows, namely one collection for each pair of objects x and y. So we will have a collection A, x, y of arrows from x to y for each objects x and y, for each two objects x and y. And then, once we have those dependent arrows, or dependent collections of arrows, we can encode the composite. Well, the composite is only defined for an arrow that goes from x to y, and an arrow that goes from y to z, where I have fixed x, y, and z in advance. Okay? So instead of having composition as a partial function, I have composition as a dependent function. And similarly, this dependent collection also encodes the source and target of the identity arrows, in the sense that for each object x, we postulate the existence of an identity arrow in the collection AXX. That means the identity arrow will automatically be an arrow from x to x. Okay. Now, I will not go very deeply into this, but if we add some logical connectors to this, say, domain-specific language, then we get a language that is dependently typed or dependently sorted and allows us to do category theory without ever mentioning equality of objects. It's a theorem from the 70s, proved independently by Fried and Blanc, that any property of categories that can be expressed in a second order, two sorted, so I have two sorts, objects and arrows. First order logic is invariant under the notion of equivalence of categories, if and only if it can be expressed in this dependently typed language, where equality is allowed for arrows, or the use of equality is allowed for arrows, but not for objects. Okay? And also, it is worth mentioning that this equality will always be an equality between two parallel arrows. So I will always ever compare arrows only between two same objects. One can ask, what about constructions on categories? Is there a similar result? And what about other mathematical structures? And this I will explain in the second part of my talk. So this is a preview of what will happen in the second part. In the Univalent foundations, we can prove a similar, an equivalence principle in analogous to the one that I've just shown you for categories, for a variety of structures, namely for sets, for groups and rings and categories. And this equivalence principle will not only apply to properties, but also to constructions, in the sense that any construction or any structure on an object will suitably transport along equivalence of objects. Okay. So, I will start with giving an overview of univalent foundations or of univalent type theory. This will be mainly a complement to what Thorsten Altenkirch said earlier today. I will be working in type theory, so everything I will say from now on are theorems in type theory, and more specifically in the type theory that I present on this slide. Okay. So Thorsten introduced the notation for inhabitants. So we have terms and types. We have dependent types. So here B is a family of types dependent over terms in A. The sigma type is the type of dependent pairs where the first element is an element in A and the second element is an inhabitant of B of the first element. And as a special case, we get the binary product. I think Thorsten did it a bit differently this morning. This product can be obtained also from this dependent product. This is what Thorsten said this morning. We have the product type, which is the type of dependent functions that goes from, A to B of the input. The coproduct type is not strictly necessary since it can be encoded as a sigma type. And then we have the identity type and a universe that I will explain later a bit more in detail, and a few base types, natural numbers, booleans, the singleton type, and the empty type. I will also assume a few axioms in the type theory that I'm working in, namely the axiom of function extensionality and the univalence axiom that I will also explain in more detail in the following. Okay. This first ingredient that I need is what Vladimir talked about yesterday, is called transport. So if we have a family of types B over a base type A, then we can construct a function of the following type, namely, if we have an element in B of A, and we have an equality or an identity from A to B, then we get an element in B of B. What this means is that if we think of B, or capital B, of a predicate, a logical predicate on A, then A satisfies B. If A satisfies B and A is equal to the tiny b here, then also tiny b satisfies the logical predicate B. Okay, so this is exactly this indiscernibility of identicals that I had on the first slide. Another ingredient that Thorsten already mentioned is this hierarchy of types. We say that a type is contractible, a type A is contractible if we can construct a term of the following type, of this type, namely if we can prove, let's say, that A firstly is inhabited, it has we can exhibit an inhabitant of A, and secondly, all inhabitants are identical to this specified inhabitant. So one can say that A is contractible if it has exactly one element up to propositional identity. And A is a proposition, then if all the identity types are contractible. So what this means is that in particular, all the inhabitants of A are identical, are connected by a path, if one wants. And A is a set, well, if the elements of A are equal in at most one way, or are identical in at most one way. Here is actually an instance of something that I will explain later only. U is a universe, it's a type of types. So there's a type of types. Maybe this will come later. No, it will come later. Sorry. We have a type of types, and this type is called U. It's called a universe. It's where as soon as I postulate the existence of a type, I have to put it in a universe. And this universe is a type just as every other type. Well, modulo some details that I will explain later. And here I actually have a typo. This should be a capital X. So we define propositions. The type of propositions are those types in the universe U for which I can prove that they are actually propositions. Okay? And similarly, sets are those types in the universe U for which I can prove that they are sets. Morally, since U appears here as a free variable, I should say that these are propositions of the universe U, so this should be prop of U, and this should be set of U. But for the purpose of this talk, I will only talk about one universe, whereas we know that we need actually a hierarchy of universes in order to avoid paradoxes.
Question?
Yes?
In your top definition, it is contractible. So I assume y equals x as the identity type for between x and y. Does it follow from what you have there that the identity type itself is one element and the identity type among those elements is one element? Does that follow from what you have?
I think so. What you are referring to, I think, is that H levels are cumulative. That means that whenever a type is contractible, then also its identity type is contractible, and the identity type and so on is contractible.
Right. How does that follow from that?
Yeah, thanks for helping me out here. It's a proof. It's not. It is maybe not very intuitive. I cannot explain it in a minute. I would also have to think about it. All those proofs of involving identity for me are highly unintuitive. So I'm very happy to try things out on the machine before I say them actually.
Okay. That's a fine answer.
Okay. In order to talk about an equivalence principle, I need to fix a notion of equivalence. And of course, for every kind of object that we consider, there's a different notion of equivalence. This is one appropriate notion of equivalence of types. So if A and B are types, then a map or a function, as Thorsten called them, function f from A to B is an equivalence if it has contractible fibers. What does that mean? So we say that f is an equivalence by definition if for any B the type of elements of A that are mapped to B by f is contractible. Okay, so this is the fiber of f over B, and we want this type to be contractible. So what this means intuitively is that for any B there exists exactly one A in capital A that is mapped to B by the function f. Okay. So we can define the type of equivalences from A to B as the type of functions from A to B that happen to be equivalences. With this notion of equivalence, we can understand the identity type a little bit better that we have not discussed a lot so far. If I have two functions f and g that are parallel, functions from a to b, then we can prove that the type of equivalences, the type of identities of f and g, between f and g, is equivalent, and this is the symbol of equivalence that I've just introduced as a type, to the type of functions that to each element in A associate a path from f of A to g of A. Okay, so this is actually a theorem only if I assume function extensionality. So this is, yeah, this equivalence is exactly the statement of function extensionality. If I have two pairs, S and T, then S and T, the type of identities between S and T, is exactly the same thing, or is equivalent to, say, the type of identities between the first projections and the second projections. So an identity between two pairs is actually a pair of identities between the two components. Okay? And as a generalization of this characterization, when I have a dependent pair, so S and T are now pairs of, well, an element in A and an element in B of the first element. And to compare those two, it's slightly more difficult because, well, I can compare easily the first components because they both happen to be elements in A. But the second component of S is in B of PR1 of S, and the second component of T is in B of PR1 of T, and they, in order to compare them, I have to use this transport function that, so I should maybe put some type annotation here. Maybe I can use the blackboard. So I have PR1 of S is here, and I have B of PR1 of S.
Sorry, could you write a little larger?
Yes, sure. I will start over. So this is A, and here is P1 of S. Is that large enough? Yeah. This is P1 of T. So this is the type B of P1 of S. This is the type B of P1 of T. So the second, this element here, I want to compare this, the second component of S to the second component of T, but the second component of S lies in this type, and the second component of T lies in this type. So let's think of them that they are this and this. So I cannot directly compare them. In order to compare them, I have to use this transport function that transports this element along the identity E into somewhere here. And then these two elements, so this gadget here is now the transport, so it's term on the left-hand side, and this gadget here is a term on the right-hand side, and now they are both in the same type, and I can compare them. So an identity between two such pairs is again a pair of identities. Now it's a dependent pair of identities, where the first component is an identity between the first components, and the second component is identity between, well, the transport of one of the second components and the other second component. Okay. That was the little introduction to type theory. Are there any questions so far? No. Okay. I will now explain what the univalence axiom is, and in order to explain the univalence axiom, I need to introduce universes that I've already used on a previous slide. So there is a type U that contains all types. Okay, this is a very rough approximation of what a universe is. So when A is a type, I can write A colon U. As I've already mentioned, we need actually a hierarchy of universes in order to avoid paradoxes such as a Russell paradox. And once we have it, but for the time being, for the purpose of this talk, I will just pretend that there is only one universe, and we will not care about this slight complication that is necessary. Yes, absolutely.
It doesn't contain all types. It contains all the bottom level types, because what's written there makes it look like U contains itself, and you don't want that.
Exactly. So if I have such a hierarchy UI, then UI would be an element of UI plus 1, but not of UI itself. Exactly. Once I have universes, I can consider a dependent type as a function from the base type into the universe. Okay. Also here, I should make sure that all those Bx are in the same universe, but in the same universe level. But we ignore these levels for the time being. So then, once I have a universe, there's the question: what is the identity type of two types? Okay, so, or what is the type A equals B, to use the same notation as the equal notation. And the univalence axiom gives an answer to that question. It says that identities from A to B are the same as, or are equivalent to, equivalences between A and B. Okay, this is what induced the slogan, identity is isomorphism. The thing is, we don't just want any equivalence here, we want a very specific equivalence. And this very specific equivalence should send the reflexivity term that we have here in the identity type. So it's actually more complicated than that. And I should explain something before continuing. The point is, we can define such a map. I will explain in a second how we can define such a map. A map that, for any two types A and B, maps identities from A to B to equivalences from A to B. And sorry, I wasn't planning to explain that, but maybe we can just accept it for the time being, that in order to define such a map, it is sufficient to pretend that B is actually the same as A, and pretend that we define this map only on the reflexivity proof. And by the specific way that this identity type behaves, this map that is defined only for reflexivity will somehow magically generalize to all types A and B and identities between A and B. Okay, so this specific map, this function, is uniquely characterized by indicating or by specifying its image in the case where B is A, and this proof here, this identity, is reflexivity. And when B is A, and I have the reflexivity identity here, then I will simply send this reflexivity to the identity on A, which is an equivalence. And when B is A, this is a well-typed assignment. Okay.
Excuse me?
Yeah.
Could you maybe say another time what exactly was an identity and what an equivalence?
Okay, so this identity is the identity type that Thorsten has introduced. It's it is part of this list that I had here. Okay, it's the identity type defined. There are several ways of defining this identity type. The traditional, the Martin Löw way, is to define this type as an inductive type with one constructor, with the constructor reflexivity. Another way of defining this identity type is by recursion on types, so that these characterizations of the identity type become actually not equivalences that we can construct, but become true by definition. Okay?
And by the equal sign versus ID, those are just two different notations for the same thing.
Right, yeah.
And shouldn't that be reflexivity in U, the refl A?
Well, it's refl UA. Yeah, I omitted one argument here.
Okay.
It's reflexivity. So if we think of these identities as paths, and it's a constant path in U that is constantly A. Right. And then the real univalence axiom, once I have defined this map, the real univalence axiom for a given universe says that for any A and B, this map, it to equiv, that maps identities to equivalences, is itself an equivalence. Okay. So what does this mean? If we combine this equivalence that is given by the univalence axiom and the transport map, then we obtain that if a predicate or a construction, a logical predicate or a construction, is given for A, and A is equivalent to another type B, then we obtain the same construction, or the same construction where we replace A by B, well, for the type B. Okay? Simply by replacing in this term identities between A and B and equivalences between A and B. Now, one can say that, one can say that this statement is an equivalence principle for types. Once I have equivalent types, then a predicate P, or a construction P on A, transfers to a construction or a property on B. In the remainder of the talk, I want to show how this equivalence principle on types that is given in this particular type theory as an axiom now lifts to mathematical structures. Okay. For instance, we will consider the example of groups. What are groups in univalent foundations? A group G is a pair called X and S, with components X and S, of a set X and operations, the typical group operations, multiplication, inverse, and unit element, such that the group axioms are satisfied. So this structure S here, which I call a group structure, involves or contains the operations, the group operations, to together with the group axioms. And then I define the type of groups as the pair type of, well, the type of pairs of a set X together with a group structure on X. What is a group isomorphism? A group isomorphism is a bijective function on the underlying types or sets from X to X prime that is compatible with the group structures S and S prime on X and X prime on the carriers. Okay. And then a theorem that I will show in more detail on the next slide is the following. If we have an isomorphism of groups, then this isomorphism lifts to an equivalence of all constructions on groups. That means that, in particular, that any statement, any property of groups is invariant under group isomorphism. So in this language that I'm presenting here, in this type theory, I cannot make a statement that is not invariant under group isomorphism. So how does this work? The proof of this statement uses two ingredients. It uses, firstly, that I construct an equivalence between identities of groups and group isomorphisms. This is the notion of isomorphism that I defined on the previous slide, this one. And then I use the transport function that I have shown already here that allows me to transport along identities. So, and since by combining these, I can not just transport along identities between groups, but along isomorphisms between groups. Again, this map from identities between groups to isomorphisms between groups is given by the canonical map that sends reflexivity on G to the identity group homomorphism on G. In more detail, how can one construct this equivalence? This is a slightly complex proof, but it's not, you're not expected to understand the details, but just the general setup of such a proof. So we start out with identities between groups. And by definition, this is actually, by definition, if G is the pair XS, so X is a set and S is a group structure on X, and G prime is X prime S prime, then this equivalence is just the identity, is just unfolding. By the characterization of identities between dependent pairs that I've shown you on a previous slide, such an identity is given by a pair of identities between, well, the first components, and then transports of the group structure, or the group structure S, along this identity between the carriers, and this transport of the group structure S should be the same as the group structure.
Excuse me.
Yeah.
Can you just show previous slide for a moment? I don't quite understand. So reflection, I understand, and this identity, what is exactly? On the right, on the left, I understand. Yeah.
So this one.
Yeah.
This is the identity homomorphism on G.
Identity.
So the identity group homomorphism.
So it's not the same thing as evidence for, it's not reflection, basically, no?
So this is the reflexivity proof,
Yeah.
the reflexivity identity, and this is the identity function on the carrier of G,
So
which is an
of
identity.
type of equivalence, right?
Yes. Yeah.
Yeah,
It's-
that's a
it
bit
has this type.
confusing.
Exactly.
I see. Okay.
Sorry.
Thank
Yeah.
you.
It is the identity considered as a group isomorphism. What does it mean to transport, that the transport of the group structure S should be the same as the group structure S prime? Well, it means that S itself is a tuple of several operations and several properties. We ignore the properties for the time being. It means that transporting the multiplication along this identity P gives the multiplication on the other side. The inverse, the transport of the inverse along this identity P gives the other inverse. and the unit transported along P gives the other unit. So this is all very intransparent. I still haven't explained what this transport is. There's very little intuition for what this transport does, but we can show that we have an equivalence between the types of identities from X to X prime, which are sets, and equivalences. This is an equivalence of types between X and X prime. Okay, so I can replace an identity P by an equivalence F, and then the condition that the transport of the multiplication along the identity gives the other multiplication transforms into the condition that the multiplication M taking its conjugation with this equivalence F gives the other multiplication. Okay, this is a non-trivial step, but this, when I pass from identities to equivalences, then a transport along such an identity becomes conjugation with the corresponding equivalence. And similarly, the inverse on the left-hand side conjugated with the equivalence F should become the inverse on the right-hand side, and the same thing for the unit. Okay, so this is a general outline of what this kind of how one can construct this kind of equivalence. The very same proof will, or an analogous proof will also go through for other algebraic structures, namely for rings, for partially ordered sets, discrete fields, sets with fixed point operators. This is, was first stated by Axel and then proved in the proof assistant ACTA by Cocon and Danielson. I will explain this result, or the generalization of that result in a second. But in order to express this to make this precise what I mean with many here, it's best to talk about this in terms of categories. So I will quickly talk about categories in univalent foundations and then come back to this result afterwards. So we had this result that for groups and rings, univalence lived, meaning that we get an equivalence, an invariance result for these algebraic structures. When we go to categories, the situation is slightly more complicated. For categories, we can again prove an equivalence between, identities between categories and equivalence of categories, where here by equiv CD, I mean a categorical equivalence from C to D. But we have to impose certain restrictions on the categories that we consider. So we will consider the notion of univalent category. I'll explain what that is. As a consequence of this result, we will again obtain that any construction on univalent categories is invariant under equivalence, or in particular, any property of categories is invariant under equivalence of categories. But with the restriction that it only holds for univalent categories. So what are univalent categories? Let's start with the definition of what a category is. It's more or less the thing that I had shown in the first part of the talk. A category here in univalent type theory is given by a type of objects and a dependent type of arrows. This set, I don't know why it is this font and not the other font. So this is just the sub-universe of sets, meaning that it is those types in the universe U that are sets. So we require arrows to be sets. And then we have operations of identity and composition, which are both dependent functions, and axioms postulating the categorical identities of arrows. So there's no surprise. Here, we have to make sure that our arrows are actually sets. The types of arrows are actually sets, because otherwise these things here are not axioms. So since the axioms talk about equalities between arrows, we want them to be propositions, and to enforce, to enforce that these are axioms, hence propositions, we need that the types where these identities live in are sets. Okay. And then what is a univalent category? It is a category in which the natural map, which is the same, or the analogous map to those that I've already shown, is an equivalence. So what does this map do? It maps identities between any two objects to isomorphisms. It is again given by just defining by just specifying the image of this map on the diagonal, meaning in the case where B is A and this identity is reflexivity, and in that case we map it to the identity isomorphism. Okay, so this map, we can define it for any category, and we ask it to be an equivalence in univalent categories. So one can say that this is a univalence axiom for categories, and this is exactly why we call a category that satisfies this property a univalent category.
Excuse me, is it by purpose that you write in words is equivalence rather than just using predicate?
That I don't use the is equiv here?
Yeah.
No, I mean exactly that thing. Sorry, yeah. So, as I said, these are all things that I can express in type theory, and sometimes when I use this sans serif font, I mean that these are the objects in the type theory. And this here is, I could have used this is equiv predicate. Okay, so what is the connection to the how does this condition connect to what I said in the first part, to the result by Fried and Blanc, where it was forbidden to talk about identity of objects. In a univalent category, we are not forbidden to talk about identity of objects, but since identity of objects is the same as isomorphism of objects, we don't get anything in addition. Like being able to talk about identity of objects is not helpful, because it could always be replaced by talking about isomorphism between those objects. So that's the connection with the result in the first part of the talk.
Can you go back a second to the previous slide?
To this?
No, next one. Yeah, I have it right here.
Sorry.
What is completeness here?
That's something that I don't want to mention, and it shouldn't be here, and this is why I tried to gloss over it. Is that okay? We can. I would like to talk about it later, but not for the purpose of this talk.
And completeness in which sense, you mean?
Completeness in a very technical sense of Siegel spaces. I don't want to discuss it. It shouldn't be here. Just cross it out, please. So one could ask, since univalent categories satisfy this invariance principle, this equivalence principle, maybe this is a very strong condition, and not many categories actually satisfy this univalence condition. But there are many categories that do satisfy this univalence condition. The first example, the simplest one, is the category of sets itself. So if I take as objects of my category sets and as morphisms functions between sets, type theoretic functions between sets, then I get a category And the fact that this category is univalent is exactly an instance of the univalence axiom for types, for Watsky's univalence axiom. Groups form a univalent category. This is exactly what I have shown before starting to talk about categories. And then we will see other instances. Functional categories are univalent if the target category is univalent. Full subcategories of univalent categories are univalent. So we have many categories that are univalent and hence satisfy this invariance or equivalence principle. Some more examples of univalent categories. That a preorder is univalent if and only if it's antisymmetric. So this means that two objects are the same whenever they are both, like two objects A and B are the same whenever A is smaller than B and B is smaller than A. If X is a type of H level 3 or a one-truncated type, then we can form a univalent category where the objects of X are given by the type X, and the morphisms from X to Y are given by identities from X to Y. And this is maybe more interesting for category theorists. If C is univalent, then the category of cones of any shape is univalent, and that means that in a univalent category, limits and co-limits by dualization are unique up to identity, up to propositional equality, and not just unique up to isomorphism. Okay, what are non-univalent categories? Yeah.
Do you get all comma categories or just the cones over a shape? All comma categories over two univalent.
I think probably yes. All I haven't proved it, so I want to be careful. But I think yes, this result should like slice categories are univalent when the base category is, and I think for more generally, comma categories are univalent when basically you put univalent categories in, and most of the time you will get a univalent category as an output. Not always. There are some examples, but mostly. One important property, however, or non-property actually, is that being univalent itself is not invariant under equivalence of categories. So we can have two equivalent categories, one of which is univalent and one is not. So this is maybe the smallest example of a non-univalent category. And as seen on one of the first slides, this category is equivalent as a category to the terminal category, one that has just one object. This category is not univalent, but this category is. So univalence of categories is not invariant under equivalence of categories, but whenever I have two univalent categories, then any structure and property of one transfers along equivalence to the other.
C, X, Y, it's like functor category, what? Yeah.
Here, so this is the type of morphisms from X to Y.
Uh-huh.
It is 1 for every X and Y. So I have one arrow between any two objects.
So like partial order, or pre-order,
right? Well, it's a pre-order where all the elements are related. I think, yeah. And,
okay.
And here, for instance, I have two objects, and I have, I haven't drawn the identity arrows. And this category is not univalent, because obviously, these objects are not identical, but they are isomorphic, because composition of the two arrows must be equal to the identity arrow. So these objects are not identical, but they are isomorphic. So this is an example of a non-univalent category. But this category is equivalent as a category to the one object category. I will maybe not talk about this. There is a procedure to associate to any category a univalent one. That's maybe a bit of a stretch to talk about now. So I will not discuss this, and I will go to the last point of the talk, which is the structure identity principle. An instance of which was this invariance result for groups that I discussed. And I will now quickly show how this generalizes to more to let's say a class of structures that one can define on sets. So as a reminder, the key of the equivalence principle for groups was this equivalence. That showed that the identities between groups is the same as isomorphisms between groups. And this equivalence is given by just specifying it on the diagonal, meaning that it sends reflexivity to the identity group homomorphism. And the fact that this is an equivalence, this map, is nothing else than saying that the category of groups is univalent. Okay? Now, if we look at more abstractly what we are doing, if we try to generalize, we say that a group is a set with some extra structure, and we want to abstract from this extra structure. And a group morphism is a map or a function of sets that is compatible with that structure. And somehow, as we saw in that proof that the category of groups is univalent, we used the fact that the category of sets is univalent. If you remember, we replaced identities between x and x prime, which are the carriers which were the carriers of the two groups we were considering, by equivalences between the carriers. Equivalence is f from x to x prime. So that was one ingredient, and the other ingredient was that somehow, in a sense that I will make more precise, this extra structure on sets and maps that define groups and group homomorphisms is a good structure in a certain sense. What do I mean by that? I mean exactly this. The slide is a bit hard to digest, but I will give an example on the next slide. We start with the category C. And the goal will be to define a new category, and it will, where the objects are certain objects of C with an extra structure on them, and morphisms in this new category will be morphisms of C that are compatible with this structure. More precisely, we consider a predicate P on the objects of C, and given two objects of C and extra structures A on P of X and B on P of Y, extra structures A and B on X and Y, and a morphism from X to Y, we have a family of propositions H of F. That should be a proposition. So what do I mean by that? I have a predicate, an extra structure on the objects of C, and I have a proposition on morphisms between objects that carry this extra structure. And if I can show that this proposition, firstly, is valid for, or is true for any identity morphism, and that it's stable under composition, then I call this pair PH a PH structure.
Question.
Yeah?
So H does not depend on A and B, right?
H It should, actually. That's a typo. It should depend on A and B. It should here be A and B. Yes, it should depend on A and B, you're right. Thanks for remarking that.
The meaning of H is something like a preserved structure. Right?
Exactly, yeah. So it must depend on the structures.
And what follows that is the preservation of structure must be invariant.
The preservation of structure must be?
Must be
Okay. Could you use the microphone?
Please. Could you turn your microphone on, please? Because then we can hear your question.
no, just one question.
Okay.
I think there's another short question.
Could you go back to the other side? So it would be HAA1X. Is that for all A witnessing PX?
Yeah.
Okay.
So, if the category, so suppose we have a pH, a structure as before on a category C, and the base category C is univalent, then we can form a new category, the opposite of which I will explain in a second, and this new category will also be univalent. Okay? So, objects of this new category are pairs of, well, an object of the original category together with this extra structure on that object. And morphisms between such pairs XA and YB are morphisms F in the original category between X and Y, from X to Y, that satisfy the predicate, the proposition H. Meaning that, so a morphism in this category is a pair of a morphism in the category C, and a proof that this morphism satisfies the predicate H. And here, here at least I got the indices of H right. Okay, so here we see that H does depend on this extra structure. So the theorem is that this category then is again univalent. For instance, we can, well, it might have been obvious by now that we can define a group structure, the group pH structure, which is given by, well, the type P of X, where X is a set. P of X is the set or the type of group structures on X, and HAB of F means F is compatible with the group structures A and B on, well, X and Y, on the carrier sets X and Y, which are hidden arguments here. Analogously, we can define many other P and H structures, in particular for the examples that I gave earlier for preordered sets, for discrete fields, and so on. So as a summary, the univalence axiom asserts an equivalence principle for types. So this is an axiom in the type theory that I've just shown. In other type theories, in the cubical type theories, it will be a theorem. And then this equivalence principle for types, it can be lifted to an equivalence principle for mathematical structures built out of types. And if I don't look at structures that naturally form a category, but something more complicated than a two-category or something, which is the case for the univalent categories that I presented. There is no category of univalent categories, but there will be a two-category or bi-category rather for univalent categories. Then an equivalence principle needs a restriction on the objects that I consider, and this restriction in the case of the bi-category of categories was given by this univalence condition for categories that I presented. And with this, I want to finish. Thanks a lot.
Thank you very much. We have now time for questions, and afterwards there will be some organizational announcements, so please don't run away immediately afterwards.
So just concerning this last point, so is it correct that this, say, hierarchy of groupoids, like n groupoids, it does not transport to high categorical structure, right? So they don't go together. Like you say, it works with types to just flat categories, right? As you put.
Yeah.
But if you want to high categories, so
Well, there
is no like lifting between groupoids on the one hand and categories, general categories on the other hand. That's
Well, there is a relation between the categories that I'm looking at and the age level of the underlying types. So in this case, the objects that I'm looking at, so they form a category, and they also, the type is a type of age level 1. For univalent categories, I have, there is a theorem that is actually easy, the consequence of the fact that the category is univalent, that the underlying type is a 1 type, or is of age level 3. And similarly, for bicategories,
just one meaning sets, right? Or
one meaning groupoid.
Groupoid. Okay.
Sorry. Yeah. There's also a notion of univalent bicategory, which is very complicated, and so I'm not talking about it. But if I have a univalent bicategory, then the type of objects will be a 2 type, or will be of age level 4, and so on. But if I don't restrict myself to univalent bicategories or whatever, I don't have any I can't say anything about the age level of the underlying type of objects. But let's say for the right notion of bicategory, which is the univalent notion, there is a very strong relationship between the homotopy level and the categorical level.
Yes.
The univalence has to be formulated in terms of equivalence, not in terms of isomorphism. Would you like to comment on that? Because I think that's possibly a source of confusion for people, because we're hearing the word isomorphism a lot. And often people kind of motivate univalence by saying, well, isomorphism should be the same thing as identity in mathematics, because we only care about things up to isomorphism.
Yeah.
But univalence applied to isomorphism, my understanding, is inconsistent, or gives you an inconsistent theory. So would you like to say something to illuminate this for us?
Could you start by reminding us what equivalence is?
So equivalence is there's different definitions, but one definition is by invertibility. So if in the category theory, it would be that there's a function and it has a pre-inverse and it has a post-inverse. But the pre-inverse may not be identical to the post-inverse, whereas for an isomorphism, the pre-inverse and the post-inverse are the same.
So here, in order to define what an equivalence is, we start out with what a map is, a morphism is, and then it is important that being an equivalence is a proposition. So that that type of equivalences can be considered as a real subtype of the type of morphisms. Similarly, like you were mentioning isomorphism, but isomorphism for me is always connected to a notion of morphism in a category. So, well, one can talk about isomorphism of types if one says that simply F is an isomorphism if there is a map G from B to A, such that they are inverse to each other. But since general types do not form a category, actually, this notion does not really deserve to be called isomorphism. It's not a well-behaved notion, and it is for the fact that it's not a well-behaved notion comes from the fact that types do not form a category. Yeah.
I don't know whether that illuminates anything, but for sets, equivalence is isomorphism. Okay? So in the case of sets, equivalence is exactly isomorphism. For other things, it's not the case. However, equivalence and isomorphism are actually logically equivalent. That is, you have an equivalence between two types if and only you have this dirty notion of isomorphism, which doesn't mean it's the same, because they're only logically equivalent, but they're not equivalent. Maybe I confused everybody, but anyway.
Yeah, so another way of putting that is to say that they're materially equivalent, but they're not proof relevantly equivalent. No?
Well, they imply each other. There are maps back and forth between the two. You can, given an isomorphism, you can construct an equivalence.
Right, but isomorphism is not a mere proposition, or not a proposition,
Exactly.
whereas equivalence is.
Yeah.
Yeah, and under univalence, you can prove that the thing in univalence is a mere proposition. So in the case of isomorphism, that then gives you a contradiction.
Yeah, I'm not sure how to derive this contradiction. I don't know.
Me. Sorry. Yes. So when you in the definition of univalence, if you replace equivalence by isomorphism, you can actually prove univalence, and then the fact that isomorphism is equivalent to equivalence is simply false, and you can find a counterexample, and then you prove true equals false, which is obviously a bit of a problem, I think.
Sorry, there was another question.
So my question is on this property of a category to be univalent. So it seems to me that being univalent for a category simply means it is some category modulo isomorphism. So this is basically in the direction of that previous question. So do I get it right that if I take any category and consider the objects up to isomorphism, I get a univalent category? So univalent just means we consider objects up to isomorphism. So is this all univalence is about in this categorical setting?
No, there are counterexamples. That's what you were talking about. It's called skeleton, right? Skeleton. And examples are clearly different. So.
Yeah.
But I heard the word clearly, but I don't see what you're talking about. So, so my concrete question is, if I take any category and consider the objects up to isomorphism, do I always end up with a univalent category, yes or no, or unknown?
I think yes, no, but not the other way around.
But not all the examples are of that kind.
Ah, okay.
So, I mean, the examples here are clearly not of that kind.
Well, what do you mean by the other way around?
Not all univalent categories are skeletal.
Okay.
So here I mean that they're objects from the set, right? They're equivalent thoughts. Okay. Objects after equivalent from the set. Is that what you mean by skeletal?
So there's other...
Actually, I don't mean anything by skeletal. I wasn't going to talk about skeletal categories. I'm not sure what skeletal here means. Skeletal is a notion that is inherently bound to set theory, to categories defined in set theory for me. So I'm not sure what the right notion of skeletal category is in type theory.
I mean, when talking about objects after equivalence, one could say that as the right notion of objects after equivalence is that what you skip this completion, right? And alternatively, one can try to somehow truncate that.
No, I think skeletal here just means that every equality of objects is a proposition. That's the definition of skeletal.
Right, yeah, okay, now I understand. Yeah. Then, indeed, objects of the category form. Well, if I have a skeletal univalent category, then objects form a set.
Is this a follow-up question or a new question?
Can I respond to it? I think the difference is that a category is univalent if you prove that the isomorphism in it is equivalent to equality in the way that we did for groups. You can think of it as a separate proof, whereas you might think of taking the objects up to isomorphism is a computational step that happens after you've considered them up to isomorphism. So it changes it, and it may have to do with the rest completion where you add in equalities.
Yeah, exactly. In the rest completion, I go the other way around. I change the underlying type of objects, adding identities, as many identities as I have isomorphisms. So I blow up, instead of going down, I kind of blow up the type of objects. Yeah.
There was another question there.
I have a rather general question about the way you treat categories, because if you look at the category introduction book, you won't necessarily find types in there. So you have introduced the types in the definition of categories in order to bring this univalence principle in, so you can have this equivalence relation between categories which wasn't there without the types. Did I get this right?
Well, types or dependent types are important earlier already. Here I use dependent types. And the use of dependent types here allows me to discuss composition of arrows without using a hypothesis that the source of one arrow is equal to the source, the target of the other arrow. Here I simply have three arguments, A, B, and C, and I duplicate so B is the object in the middle, and I duplicate it, I put it here and here. And by this duplication, I enforce that the arrows that I plug in here are compatible. This is where this is why dependent types here are important. Could you use your microphone, please?
This could in principle be stated in terms of a type of arrows mapped into a product of types of objects, but then we would use some dependent product thing here, right? So
yeah,
the condition would be more complicated to state, but it's in principle.
One can kind of simulate this in set theory somehow, these dependent collections or so. Is that what you mean? I mean, also in set theory, I can define something like hom A, B, that would use some, yeah.
I mean, anyway, a dependent type is the same thing as a type over O times O, so one could in principle formulate in terms of a type of all arrows.
Yeah.
But that would be, okay, that would be messy.
There is another question over there.
Could you make it precise again what lifting univalence to such a category means? What lifting univalence to groups means? I don't know, maybe you noted it.
Well, it means, what I mean really by this result is I haven't written it down really, but what I mean by this result is a term of the following type. Well, for groups, if G and G prime are two groups, then what I mean by lifting an equivalence principle is a term of the following type that one can construct, well, given a P, a predicate on groups. Then I get a map or a function, that takes as input an isomorphism between groups, and yes, and a proof or a construction, or a construction of type P on G, and gives me the same construction or analogous construction of a proof of a property on G prime. So this one can say is the equivalence principle on groups for this particular predicate P. So I should have an argument P here. Oh.
That should be functorial, or?
What do you mean by functorial?
Yeah.
Sorry, I messed this up with the blackboard. But of course, EP, it's an equivalence principle for groups, and it should exist, of course. It is independent of the particular predicate.
Oh.
Does this answer the question? So this is the formal statement, if you want, of equivalence principle.
Okay, so before getting to the organizational points, maybe let's thank the speaker again.